All right. So last hour we already learned how to build a logistic model, right? By means of building a logistic model, actually we are estimating a set of coefficients, right? Isn't it, right? So you can so we basically can estimate the coefficient, okay? So basically using the same way as we have done last week in linear model. They are not very difficult to do that. But after you have this coefficient, when you want to use this coefficient to calculate the probability of y equal to 1, there are some mathematics details, okay? You don't really need to know the detail about this mathematics, but you need to know some of the basic knowledge before you can interpret the coefficient correctly, okay? So let's take a look at this, right? See, before anything, let me introduce a few terminology, right? That it's related to logistic regression, okay? Usually when we talk about probability, we use probability, right? And we denote probability by P, okay? But actually probability has three different ways. So there are three different ways of measuring probability, okay? Probability is one. The second thing is called odd. Now odd equal to P divided by 1 minus P, okay? So if P is a small value, for example, if P is like 0.1, sorry, if P is a very large value, for example, like P equal to, sorry, let me say that again. So the odd is actually, when you do a gambling, right, the ratio that between your bet and the award, okay, and it's called odd, okay. If I bet like Saudi Arabia would win Argentina, right, the odd will be large, right, because probability is small, right. If I bet the Argentina would beat Saudi Arabia, the odd will be like just a little bit, right? Because the probability is big, right? So odd is just another way to express probability, okay? And the formula is like this, right? So for example, if you have a odd, if your probability is 0.9, okay? 0.9. If P equals 0.9, what is the odd? No, do it again. P equal to 0.9. So 1 minus P equal to 0.1. And this is 0.9, right? So the odd is 9, right? The odd is 9, okay? So if your probability is 0.99, what is the odd? 0.99. 99, right? Odd is 99. So what if your probability is 0.9999? Yeah, the odd become 9999. So odd could be very, very high, right? Right? So if the probability that you will win is very small, your odd is very high, right? Isn't it? Okay. So this is the calculation between odd, P is always between 0 and 1, right? And odd could be from 0 to infinity. Is that it? Right? Okay. So, and because odd run from 0 to infinity, if we want to confine it to a finite range, we will apply a log transformation on odd. This is odd, right? If I apply log transformation on odd, it's called log it. Okay? So if you have P, you can calculate odd. If you have odd, you apply logarithm transformation, then you will get a term called log it. Okay? So I can say the probability of y equal to what? I can say the odd of y equal to 1. I can say the log it of y equal to 1, right? They are all measuring how likely y would equal to 1. So there are three different ways in calculating probability. They are the same thing. It's kind of like sometimes when you are measuring weight, you are using kilogram. Sometimes you are using ounce, right? And when you are measuring length, sometimes you are using meter, centimeter. Sometimes you are using feet, right? So it's the same idea, right? There are different units to measure probability, and there are simple mathematical relationship between themselves. Okay. The point is, the reason that we want to introduce this terminology is the value of the linear combination when you are doing logistic regression. The value of this linear combination is actually the log it of y equal to 1. It's not probability, it's log it. Okay? And in order to transfer the log it into probability, you need to apply this function, which is the logistic function. Okay? That's some mathematical complication. Not very complicated, but you need to know, right? Before you can use the coefficient to calculate the probability. Okay. So so here in R, it's actually in my own experience, I feel that in R it's actually easier to do this math, right? Better than using the mathematical notation, right? See, you have the coefficient, right? You have the value of x, right? So you can get the value of linear combination. And as I told you, the value of this linear combination is the log it, right? It's not the probability. If you want to transfer log it into odd, you do exponential, right? Because log it is odd. Remember this? If you apply log on odd, it will be log it, right? So you have log it, you want to transfer back to log. You do what? You do exponential, right? Because that is the inverse function of log. So I do exponential on this log it, I will get the odd, right? And I use this simple mathematical transformation to transfer odd back to probability, right? So in this way, when you have the x, you can calculate first of all the log it, secondly the odd, and after all we will get the probability of y equal to 1 is like 0.128, okay? But actually you don't really need to do this by yourself, right? You can call the predict function. Predict function will calculate the probability for you directly, right? So just in case you want to do that, you need to do this. So this is just another example, right? So The benefit of writing program is that you only write the program once, right? And you can run the program again, and again, right? See, you extract the V, and for any given combination of X, you can calculate the log it, the R, the probability of Y equal to 1. Get it? Okay, so that is basically the basic idea about logistic regression. Any question up to this point? Okay, now let's move on. Okay, so we don't need to plot the logistic regression line, right? In the perspective, in the aspect, for the sake of a practical application. Usually you don't need to draw the regression line. Usually you don't need to draw the regression line, the logistic regression line, right? But just for better understanding, right? I draw the line for you, okay? Just for better understanding. You don't really need to worry about the code chunk. You don't need to do it usually. Yeah. I just put on a plot for better understanding. Right? Okay. Here we have 3 variables, right? We have x1, we have x2, and we also have y, right? Isn't it? Right? Okay. Now, where is y in this plot? This is x1, right? Every point is again a data point, right? And the x horizontal and vertical coordination of the data point is x1 and x2, right? So what is y represented in this plot? Can you guess? Now, y is a binary variable, and it only takes 2 different values, right? So, what is y? How y is represented? Yeah. The color, right? Y is right now the color, right? So what? And where is the model? Where is the regression line? It's still here, right? This regression line is actually, if you set this expression equal to 0, right? When this thing is equal to 0, it would map into this line, okay? So this line actually corresponds to this line actually corresponding to this point, okay? Because this linear combination equal to 0. If in the plane of x1 and x2, right? We draw the regression line, right? By setting the linear combination to 0, okay? And which means that in every point along the line, this linear combination equal to 0, right? When this combination equal to 0, f of x is 0, right? Which implies that the probability of y equal to 1 equal to how many? I mean, when f of x, when this linear combination, the value of linear combination equal to 0, what is the probability of y equal to 1? Yeah, louder. 0.5, right? So what this regression line means is that it is trying to, like, in the plane of the predicting variable, in the space of predicting variable, it tries to, like, draw the line, right? So above the line, the y equal to 1, the probability of y equal to 1 is larger than 0.5, right? And below the line, the probability of y equal to 1 is, like, less than 0.5. It's more likely that for every point that above the line, it's more likely that y equal to 1, right? For all of the points that below this line, it's more likely that the y is equal to 0, isn't it? Right? That's how it works, right? That's how it works. So the GLM function is just like the LM function. It will try to find a linear, find a line, right? Finding this coefficient is like drawing a line on the space of the predicting variable, right? And try to separate the different type of y as distinctive as possible, right? Of course, there will be error, right? So that, for example, at this point, right? There are error. The model cannot be precise 100%, right? But the algorithm will try to find a line that separate different color of y as much as distinctive as it can, right? And that algorithm is out of our scope, okay? It's already encapsulated in the GLM function already, okay? So if we go back to our notebook, this is why I plot a line for you, right? I told you that you don't really need to know how to do this, but in R, we can actually write a few lines of code to do that. And then because of time, I don't have enough time to explain the code for you. But actually, besides the line of probability equal to 0.5, we actually can draw a line of probability equal to 0.6, 0.7, 0.8, 0.9, okay? The same way we can draw a line of, this is the probability of y equal to 0.4, 0.3, 0.2, 0.1. See? Okay. So, and again, this is why we want to, this is the reason that we want to build a model, okay? When we only have the data, the data only occupy a very small fraction of the space, right? But as long as we have the model in every combination of x1, x2, for example, I point here, I know that if x1, x2 is here, then I know that the probability of y equal to 1 is how many? If I know that the x1 and x2, the combination is here, right? Then the probability that y equal to 1 can be estimated as what? I told you that this line is actually probability of how many? This is 0.5, 0.6, 0.7, and here is 0.8, right? Whatever x and y all of the x1, x2 combination that lie on this line would predict the probability of 0.8, right? And here is 0.9, right? And likewise, I can say that something here is like 0.85, right? And here is like 0.75, something like that. Right? For every given point in the space of X, I actually have the prediction value, right? Isn't it? So the model is kind of like the data is finite, isn't it? But as long as you build the model, you can do the prediction on the entire space of the prediction variable, isn't it? Right? That is one of the reasons that we want to build model. Right? Model is not always good, always right, but it gives us a method to predict what we do not know, to predict what we do not have, right? By what we already have, right? That's how model works, okay? So so I don't really want you to like learn how to make this plot, but well, this plot will help you understand how linear model works, okay? And the rest of the code is just to plot these functions, okay? This is the function of transforming P into R. As I told you that P is always between 0 and 1, and R can be from 0 to positive infinite, okay? If you apply log transformation on R, and it will become like, right? Because 0, if you apply log to 0, it would go to the negative infinite, right? And this, if we transfer P to log it, okay? But usually, the most useful transformation is I want to transform log it back to probability, right? This is log it, which is the value of the linear combination, right? So the log it is the value of the linear combination. And usually I want to transfer this log it back to probability. And this function form is called logistic function, okay? And the thing that you need to remember is when log is 0, probability is 0.5, okay? And when the log is lower than -5, it's already the probability is close to 0, and when the log is larger than 5, the probability is close to 1. That's the thing that you need to remember, okay? And that's all for the first notebook, okay? Any question? It's good enough, huh? It's good enough, okay. Now let's take a look at the second notebook. Now we want to take a closer look at the coefficient, okay? That's the purpose of the second one. Again, let me read in the data, okay? Let me read in the data. What? It's a little bit strange. Okay, let's take a look at the data. It died. Okay, is it good? Okay. Now we have a data set like this. This is actually a data from an insurance company. Okay. The purpose of this data is to is to predict the quality of care for some diabetic patients. Okay, because we are medical insurance company, right? We are so we have the medical record of some of our insurance customer, right? And some of my customer has diabetes, right? Diabetes is a very dangerous. Unfortunately, a lot of people have diabetes, right? And diabetes, actually, if you take care of it carefully, right? It can. You can have diabetes, but if you control it good, then usually you can last for a very long time without serious problem, right? But if you do not take good care of these diabetic patients, right? Sometimes it would have a lot of very bad complication. Like sometimes you need to cut your leg. Sometimes you need to your eye would you go blind or something like that, right? So the diabetes is a thing that if you carefully take care of it, it will be good. But if you do not take care of it, then if you have a poor care condition, then it's very dangerous. Okay. So this data set is trying to evaluate the probability of poor care. Okay, I have the medical record of every patient. We don't have too much data. We only have 131 data, right? So for each of this patient, I have their medical records. The member ID is not useful because it's just the ID, right? So, and this is the inpatient days, ER visit, how many times, office visit, how many times, and so they are different measurement, right? according to their medical records. I have the medical records, and I want to use this record to estimate the probability of poor care, right? So if this patient is poor care, I can do a lot of things, right? Maybe I can send some, maybe I can like dispatch some social worker, right, to help them, right? Maybe I can dispatch a nurse, try to improve their caring condition, right? That will cost me money, right? There will be a cost. So I need to evaluate. Maybe I have like 2 million in the United States, right? Some of the insurance company may have like millions of diabetic patients, right? So if I can have a model to predict the quality of care of all of my diabetic patients, right? So maybe I can set up a strategy, right? So I can intervene, right? For those who do not have a good care, right? That's the background of this data, right? This is important because we will use this data for this week and next week, okay? So I let you know more about its background, okay? Okay, so I have this variable, and I want to build because the poor care is actually a binary variable. Okay, you can see that. The poor care is already encoded at 1 or 0. Well, 1 means poor care, right? So I want to predict the probability of poor care for each of the patients. Okay. Well, so after I get the data, as I told you, the first thing is I want to know this, right? I want to know the proportions of poor care, right? Okay, the proportion of poor care is like about 25%. Okay, so but that is the average. As I say, that is the average probability of poor care, right? With the model, I want to evaluate the probability of poor care for every individual, right? For every individual patient, okay? So back to, let me see if I have a slide for this one. Okay, let's take care of it later. Now, again, if you still remember, before we build the model, actually we want to split the data, right? Still remember that when we do the linear regression, right? So nowadays, if we want to build a data and try to evaluate the accuracy of the model, right? We need to like kind of reserve some data to measure the predicting accuracy of the model, right? So we cannot use all of our data to build model, right? So we need to do a split, okay? Usually we'll use this sample split function, and you need to specify 2 things. First of all is the ratio of split, okay? You want to split it into 70% for training, 30% for testing, right? And besides the splitting ratio, you also need to let the function know your target variable, okay? The reason that you need to give it the target variable is that when you do the split, it would try to keep the ratio of poor care in the training and the testing subset. Okay. If you just split it into like 30%, 70%, right? Sometimes the proportion of poor care is different between the two subsets. You don't want that happen, right? You want to do that when you split it into two subset. The distribution of poor care are actually similar to each other, right? So that's why you also need to give it your target variable. It would make sure that the training and testing data set would have the same proportion of the same distribution of the of your outcome variable. Okay, so we can like do the split. And after you call the split, you will return a vector, the splitting vector. The vector is a vector of true and false. Okay, and usually true is the training set, right? We use true. We subset D with split equal to true and put it in TR. We subset D with split equal to false and put it in TS, right? Okay, so as you will see that. There's a bug here, I think. Okay, so after I split them, I will have like a training data and I have testing data, right? Okay, and then I can see. So I actually see the proportion of poor care equal to 1, right? In the D data set is 2519, and in training data set is exactly 25, and in testing data set is 2564, right? Okay. So not only that it would cut it into 0307, it will split it, and it will make sure that in each of this subset, the fraction of poor care is the same. Okay. It's not exactly the same because our sample is actually very small, right? Okay, so it cannot be exactly the same, but they will be very close to each other. You get the point? Okay, so this is data splitting. Okay. Now after splitting data, we can build model, right? So we use the training set to build a model, right? Okay. As I told you that here we need to call GRM, and here we need to have this extra argument, and then we can get a summary. Again, because just for demonstration purpose, I only use two variable. Okay, so the two variable, the corresponding coefficient is like this, right? And this is the intercept. Okay. Now, and you can, as we already done earlier, we can actually extract this coefficient. Okay. Now, the point that I want to, the purpose that I want to, the idea that I want to show you in this notebook is actually how to interpret this coefficient. Okay. If you still remember, the coefficient implies the in linear regression, right? Last week, okay? In linear regression, the coefficient actually imply the marginal effect of x to y, right? Still remember that? Because of this mathematical relationship, right? So if x1 increase by 1, y would increase by b1, right? So it's kind of like a marginal effect, right? But in logistic regression, it's a little bit complicated, okay? Because this linear combination do not apply to the probability of y equal to 1 directly, right? It actually applies to the logit of y equal to 1, okay? So the coefficient that we get from in the logistic regression, it's actually right. You can say that it's the marginal effect of x to the logit of y equal to 1. You can still say that, right? But it's not the marginal effect to the probability of y equal to 1. It's the marginal effect of the logit of y equal to 1. Right? That's why we need to introduce logit R, right? In logistic regression, because of the transformation, the coefficient is no longer the marginal effect of x to y, okay? Basically, it is simply put, it is the marginal effect of x1 to the logit of y equal to 1. Because if x1 is increased by 1, right? The logit of y equal to 1 would increase by b1, right? Isn't it? Okay. But logit is a very, very difficult concept to businessmen, right? Very few business managers know what it means by logit, right? So you basically have to do some transformation before you can actually use it in a business context, right? Okay. I mean, mathematically, this coefficient is the marginal effect of x to the logit of y equal to 1. But logit of y equal to 1 is like a very, very difficult term for most of the managers. Managers do not know what you say, okay? So usually you need to transform it into probability or transform it into art at least to interpret the coefficient. You get my point? Okay. So let's do some real practice. So for example, I have this B2. So I know that it is the marginal effect of art, right? It's the marginal effect of sorry, let me say that again. This is very tricky here, right? So this B2 is actually the marginal effect of x2 to the logit of y equal to 1, right? So if logit is actually log transformation of R, right? So before I can go back to probability, I need to go to R first, right? So I apply exponential to the coefficient, right? So if I apply the exponential to the coefficient, this is actually the R ratio, okay? Which means that if x2 is increased by 1, B2 actually correspond to this one, right? If the office visit is increased by 1, then the odds ratio of pool care would become 1.0848, okay? Which means that you cannot use the coefficient directly, okay? You need to apply exponential to the coefficient, right? And after you apply the exponential to the coefficient, it's still not the probability, it's up, okay? So if you apply exponential to the coefficient, you will get the R. The multiplier of R, I should say so. There's one thing that you need to know it very carefully, right? Right now we are talking about the multiplier of R. It's not the addition of R, okay? It's the multiplier of R. Because R by itself is a ratio, right? So, if the office visit is increased by 2, then you need to like, it's not like you need to like do a power, raise the power to 2, right? So this is the arc multiplier if office visit is increased by 2. Okay? You got my point? See, so by 2, the arc of y equal to 1 is multiplied by that. Okay, and let's see another one. The B3 is corresponding to norcotis, right? So if norcotis is increased by 1, and then the arc of y equal to 1 would be multiplied by this thing, 6%, or raised by 6%, you can say that. And then if norcotis is increased by 1.5, you see that this is not multiplier, right? This is actually, you need to raise it to the power, right? Okay? Because we are talking about multiplier, they are not additional, they are not additive relationship. They are multiply type of relationship, okay? So the value of x is here, okay? And this is the coefficient, right? You basically need to use this type of transformation to interpret the marginal effect of predicting variable to the arc of y equal to 1. See that? Okay. That's what I express here. This coefficient cannot, it actually is the marginal effect of log, but log is too difficult to understand, right? So usually you will like kind of apply exponential transformation to the coefficient and treat that as the arc ratio, the arc multiplier of y equal to 1. Okay? See that? So because they are multipliers, so their effects are actually multiplied by each other. Okay? So if you smoke one more cigarette, and you have your probability of getting cancer is increased by 10%. If you drink one bottle of wine, then your probability of getting cancer is increased by 10%. And then if you drink and you smoke, right? The effect is not 20%. The effect is 1.1 multiplied by 1.1, which is 21%. You got my point? Okay? So The detailed calculation could be quite complicated, and I don't really have time to cover every detail, right? The one thing you need to remember is the coefficient need to be take exponential, right? The second thing is that it is actually the odd multiplier instead of the incremental probability, okay? Two things, okay, before I end this class. Just remember these two things, right? Coefficient need to be take exponent transformation, right? And it will be the multiplier of odd, it's the odd ratio, okay? And because they are odd ratio, so their effect are not additive. Their effect are multiply to each other, okay? That's the difference between logistic and linear regression in terms of coefficient interpretation, okay? Because of time, I cannot, actually I can like spend like 1 more hour for coefficient interpretation, but unfortunately I do not have time to do that, okay? But you need to remember these two things, because these two things are very important for using logistic regression in business, okay? Okay, let's take a break and let's be back in 10 after 11.